Well, good afternoon, everybody. Last but not least, I hope. And I'm very grateful to the previous speakers because they've set the scene beautifully and induced a little bit of terror in the audience, which always helps as well. So I don't really know very much about the sun. I'm a space physicist, so I study the environment around the planets, particularly the environment around our own planet, and then also the environment between the planets, and how that is really controlled by the sun, but how it interacts with those planetary environments. And so, to begin with, I'm going to just show a movie of the kind we've seen several times. So we really don't need to recap this. We're looking at the sun. The sun is very active, and it is continuously emitting material into the space environment. So this is the solar wind we've heard about. And the solar wind means the sun is losing a mass of about 1 million tons per second. And that is streaming off into the space environment, streaming out through past the planets, and it's there all the time. So the solar wind is a 24/7 phenomenon. But on top of that, we see these coronal mass ejections. So in this particular movie from the Solar and Heliospheric Observatory, where we see another one of these planets and a comet disappearing into the sun, you can see that there's this background of particles streaming out from the sun all the time, the solar wind, but every now and again it looks like a gentle puff of material coming out there. There's one has just occurred. Several more happened during this movie. But we have to keep remembering those numbers that Lindsay quoted. That's 1 billion tons of material leaving the sun at 1 million kilometers an hour, being fired off in virtually any direction, but some of them will head towards the Earth. So really the takeaway message here is the sun is constantly emitting material, and you can detect it all the way to the edge of the solar system, to the heliosphere, the sphere of influence of the sun. But every now and again, it will emit an explosion. There will be an explosion emitting a big cloud of material into the space environment. And those are often accompanied by flares, which are the radiation. It's a bit like a solar flash gun going off. So then, what does this do to us here on Earth? Well, the most obvious answer is the one that probably most people know about already. If you travel to the high latitudes in either the northern or the southern hemisphere, then in those months of the year when the sun sets below the horizon at night, the sky gets dark, and then we're treated to these spectacular light shows. So here we have some time-lapse photography of Aurora Borealis, another beautiful mix of Greek and Latin, in the area, in the border between Finland and Russia. And so what we can see here are these dancing lights in the night sky, these green colors. You can see here they're above the clouds, so the clouds get in the way rather annoyingly. They're actually occurring at altitudes of about 100 to 200 kilometers above ground level. And these are, as I said, time-lapse photography, so you can go and type Aurora Borealis into any search engine, and you'll find lots of movies of this kind. And they're really showing you, or giving you an impression of just how dynamic these features are. But you can see the clouds are skidding across the sky very rapidly. The stars are wheeling in the sky as the Earth rotates. So this is not the kind of motion you would expect to see with your own eyes if you were fortunate enough to see a display of the Northern Lights. This is very much accelerated. I estimate at a factor of about 50 here. So there's probably about a minute going past every second or so of movie here. So in reality, they look very different. So if you're fortunate enough to go and see a display of the Northern Lights in with your own eyes, then you're probably going to see something that looks a little bit more like this. And I'll set this movie running. This is the Northern Lights over the Skagafrost waterfalls in southern Iceland. And you can see here there's a much more gentle and ghostly quality to the kind of movements in the Northern Lights that you just don't get from those time-lapse movies. It's much more mesmerizing. It's quite hypnotic. It is quite ghostly. And it's not surprising that people would see images or see features like this in the night sky and start to attribute them with quite spiritual or religious significance. And so I have just a couple of these movies. So here we see a red and green aurora, again over Iceland, and I think that's Venus glowing brightly in the night sky. And that's actually a movie. It is moving. Those pillars of light are actually gently moving around in the night sky. And so it's not surprising at all, really, that many indigenous people in the part of the world that are beneath these beautiful light shows put on by Mother Nature attribute them to a spiritual origin. And there are many legends around the world at what we're looking at here. Most of them involve the next world, the afterlife, often involving battles, so we might be seeing the souls of dead warriors in the afterlife, possibly the souls of people who died in some awful form of misadventure. And so there's a connection that what we're seeing here is a glimpse into another world. And actually, it's not surprising, as I've said, that if you were living in the tundra in the Arctic Circle, or if you were living in a nomadic lifestyle like this gentleman is, where you're very connected to the environment, you're sleeping basically outside at night, you would see the Northern Lights many times a year, many times a week, probably. And so there'd be your people would come up with lots of legends, just like we have stories about what makes the crops grow at a particular time of year, or we would have done hundreds of years ago. In ancient Egypt, everything's linked to the sun and the sun gods for obvious reasons. So these indigenous people would have had a whole mythology and a folklore and a culture built around it. And there are actually some very interesting legends. The one I find particularly illustrative in so many sociological levels is the one that the Northern Lights are actually the hands of young maidens who've gone to their death early, and they've gone to their death before they had the satisfaction of being married. And they're waving from the afterlife as a warning to young girls that they should get married before the same fate awaits them. And you can't help feeling that it was the guys who made that one up. But it actually cuts through art and literature across the decades, across the centuries. And even now, people are very, very interested in seeing the Northern Lights. I occasionally do work with some travel companies who take people to see the Northern Lights. And there are some things you can do to increase your chances of seeing the Northern Lights here in the UK. And my final slide is going to be to tell you a little bit about how you might go and try and do that yourself. And it really comes down to the juxtaposition between the kind of Northern Lights you would see in the Arctic Circle and the kind of Northern Lights you might see here in Scotland are that they're caused by slightly different effects. And the Northern Lights that you'd see at the edge of the Arctic Circle are being driven by interactions mainly with the solar wind, which are there most of the time. So if you go up to the Arctic, or if you go to the Antarctic to see the Aurora Australis, those processes are going on most of the time. So any given night, if you've got clear skies and you've got darkness, there's a reasonable chance you'll see something. It varies, but if you're there for a couple of weeks, you'll almost certainly see something. Here in the UK, it's a little bit more rare, and we're actually to spoil the story, as it like, to spoil the ending, what you really need is one of those coronal mass ejections to hit the Earth's magnetosphere and impart loads of energies and bring the Northern Lights to much lower latitudes. And so here you can see this fantastic image of the Northern Lights in my part of the world, in the English Lake District, very clearly there. And so you do see them from lower latitudes, but there's a trick to doing it. And I'll try and say something more about that later. Now, as I've already mentioned, the Northern Lights have spawned lots of interesting effects on culture and media and literature and art and religion. And I quite like this image because this is actually an image of the Northern Lights over Central Europe in the 16th century, if I recall correctly. And what I particularly enjoy is the fact that the Northern Lights are creating this magnificent display over the night sky. And the politician has come out, this is the mayor or the governor, and he is coming out and commanding the aurora to recede, because these things were generally thought to be portents of doom. Bad things were going to happen. You can imagine anything bad you care to think of, this is an indication of it. You can see over here the scholars are consulting their scripts and obviously advising the government on what to do. And then over here you have the townsfolk who've fallen to their knees and are praying for forgiveness and for things that and hoping that terrible things don't happen. And actually there is some excellent contemporary evidence of what were almost certainly auroral displays over Central Europe, where they probably occurred once every 30 years or so. So we're talking about once in a generation at this time. And the countryside basically emptying as folks went to the cathedral cities to undertake acts of penance and pray. So there's some really interesting sociological things going on to do with the aurora, and it carries on right through to today. So that's a rather old image. Here's one I rather like. So would anyone, this is a document, a very modern document. Would anyone in the audience care to guess what kind of document this might be? A passport, yes. Okay, no fooling you guys. This is a passport. It's the internal pages of a passport where the folk in the chap in the booth at the airport stamps it, will put your visa in. But it's not a UK passport, obviously. It is, in fact, a Norwegian passport, the new Norwegian passport. And you can see in this this kind of printing that you would see also on banknotes to avoid scanning and photocopying and duplication. You can see here there is a beautiful Arctic scene of a fjord with the huge mountains either side, and you can see the sun there high in the sky. What I particularly like, and you might be thinking, why is Professor Jim showing us a passport? When the person in the booth does the security check and puts your passport under the ultraviolet light, it reveals the security measures. And here we see the Northern Lights on your passport document. So, absolutely beautiful document there, really bringing through this theme of the Northern Lights and how they touch us right up to present day. So what's going on? What's the physics? Well, we've heard some clues already as to what creates the Northern Lights. We live on a magnetic planet. So deep beneath our feet in the core of our planet, the core is a mixture of different metals, mainly nickel and iron. And they're actually still molten. There is heat at the core of our planet, and the interior of our planet is hot. You can see this when a volcano erupts, hot stuff is vomited out. The heat of our planet is left over, a lot of it, from the formation of our planet. When the material in the early part of the solar system, 4.5 billion years ago or so, collapsed inwards under gravity, that falling inwards actually releases gravitational potential energy and turns it into kinetic energy. So things that were originally at rest and had lots of gravitational potential energy start falling in towards a mass, going faster and faster, and that converts the potential energy into kinetic energy, and then as it collides, that's converted into heat energy, and a lot of that heat is left over. So the Earth is very hot in its interior, and also there are radioactive elements in there which are keeping it simmering rather nicely. But that metallic core is moving. It's churning very slowly, not very fast. If I remember rightly, it's about the rate at which a fingernail grows or something like that. But that movement of an electrically conductive molten ball at the center of our planet generates a magnetic field. And the magnetic field is usually thought of as coming out of the southern hemisphere and going back around and closing in the northern hemisphere from one pole to the other pole. And if you had a magnet, I'll take my pointer. If you imagine this was the needle of a compass, which is basically a magnet, if at any point I put that on my diagram, it would align with the background field and point towards the north, which is what makes compasses, which are just little magnets on a spindle, very, very useful. You can navigate your way around the world because of this effect. So the Earth is magnetic. We can't see the field lines. We've already discussed it. They're in this room right now. We don't register that they're there at all. However, that magnetic field really controls the Northern Lights, and it brings them down to us, if you like. And this was something that was really nailed early in the 20th century. And so before that, of course, there was no real clear idea of what was out in space. We could see the sun. We feel the heat from the sun, but that was about it. We didn't really know what connections there were between the planets, because there's not much you can see. Space looks quite empty. But this fellow is a chap called Kristen Birkeland, who was a Norwegian. And Kristen Birkeland had been on expeditions up to the high Arctic, and he'd noticed that when the Aurora Borealis were active, magnetic instruments were disturbed. The needles, basically, if you have a magnetometer, that's a very fancy way of saying an electronic compass that measures the direction and strength of the Earth's magnetic field. It was known that wobbled around a bit from day to day. Over the course of a day, the magnetic compass needle will just oscillate a little bit. But if you did that when the Aurora were out overhead, there was lots of movement. There were lots of magnetic disturbances. And he supposed that it must be an electromagnetic effect. There must be electrical currents running in the upper atmosphere of the Earth, which cause a magnetic disturbance at the ground level, which his instruments were detecting. And so he went about trying to do something in the laboratory to do that. And this is what he calls a torella. This is his machine for creating the Northern Lights. And what you basically have here is, this looks like a fish tank on a very sturdy bench. It's probably because the glass is very thick. It's a vacuum chamber where you can pump out virtually all of the air inside. It's sealed, and at the heart of it, there is a little globe you can just about see there. It's made out of metal, and it's got a bar magnet inside to give it the same kind of magnetic characteristics as the Earth. And what he did is he applied a very large voltage. Experiments always sound so much better, whereas I started by applying a very large voltage. But thousands of volts of electricity at a very high current, using batteries here, he applied to this system. And you could see the gas around the globe start to fluoresce, to starting to emit light. And if I remember correctly, no, I don't remember correctly. What he could see is around the poles of this model Earth, you would create this very bright emissions, and he could control using the apparatus how that appeared. And from these experiments, Kristen Birkeland surmised that the northern lights must have been emission of lights from the upper atmosphere, and it was being caused by particles coming from space and being guided by the Earth's magnetic field down into the upper atmosphere. And he was absolutely spot on. That is basically the foundation of our understanding now of what is creating the northern lights. He was also something of a character. If you ever want a good read, go and try and find out a little bit more about Kristen Birkeland. He was nominated for the Nobel Prize 7 times, but never won it. You can see in here he has his fez on. At this time, there was an awareness of the dangers of X-rays and radiation produced by electrons hitting metal targets, and so he was probably aware that there was some radiation risk here, and so he always wore his fez to protect his brain. So he says, so health and safety is not a new thing. And if we fast forward into sort of the 1930s, it was started to be predicted that the sun must be emitting material into the space environment. And what was an early view was that normally the sun is sitting there relatively quiescent, but every now and again there would be one of these explosions of material into space. And when that happened, a front of material, a front of gas would travel out past the planets, and it would arrive at the Earth sometime later. We now know that journey time is somewhere between 1 and 3 or 4 days. But it was thought that only happened periodically, just when the sun belched out one of these explosions of material, what we would now call a coronal mass ejection. We didn't know about the solar wind at that point, that this was a steady flow that was always there. But the idea was then that the Earth would be something like a rock in a river, and that this material would come out and would be deflected around our planet. So it was suspected that there was this gas being emitted by the sun periodically. And then in the late 1950s, and this is 1957, I think, the space race was really kicking off. The Soviet Union and the USA were racing each other to put things in orbit and put people in orbit and ultimately to put people on the moon. And this is a picture after the successful launch of the first US satellite that basically hadn't exploded either on the launch pad or on its way up. So it was a very big deal because at this point the USA was behind the Soviet Union in the space race. And in the center, there is a gentleman called James Van Allen. And he's going to be a name we're going to hear a couple of times. And he was a professor at Iowa University. And he has some colleagues with him holding aloft a model of the satellite that they'd just launched. What was very interesting is they needed to put something on this satellite. They didn't really want to fly an empty satellite, although, to be honest with you, the objective of flying the satellite was to fly the satellite and show that it could be done. But never want to miss an opportunity, the scientists decided they could put in a cosmic ray detector at the top. The idea was you'd launch it, it's basically a Geiger counter. You've seen them on the movies, it goes click, click, click whenever you hear radiation presence. Well, this Geiger counter would detect radiation coming from sources in space. So you might have seen the particles coming from a supernova. So they thought, we'll put one on and fly it. And they did, aided by this chap on your right, on Van Allen's left, and that is Verner Von Braun. He was the engineer behind the German rocket program in the Second World War, who at the end of the Second World War had surrendered to the Americans. Effectively, he was given the choice, who did he want to surrender to, and he decided not to surrender to the advancing Red Army, and went to great lengths to surrender to the Americans, who flew him to the States, and basically he went on to do this kind of thing, and ultimately designed most of the kit that put men on the moon. So, James Van Allen and his team put this instrument on this satellite and launched it into space. And one of his colleagues is attributed with a really great quote. He said, "My God, space is radioactive." Because they turned on their Geiger counter, and rather than it didn't actually make click-click noises, but if you can imagine, rather than occasionally getting a tick, a little bit of data as something arrived, it was just constant noise. It was just constant data. Space was full of high-energy subatomic particles, radiation, what we'd now call beta particles and alpha particles. So these are electrons or nuclei of particles that have had their electrons stripped away. And this was a complete surprise. Space had thought to be empty, but it wasn't. It was full of high-energy particles. And Van Allen went on to map these with successive space missions, and there are some, you can see here he is on the cover of Time magazine. And this is actually from one of the original papers in 1959, and what this is supposed to be is looking at the Earth in the equatorial plane, so the North Pole is somewhere up here and the South Pole is down here. And you can see these sort of belts, of shaded belts in this diagram, showing where there are high densities of these very high-energy particles. And they were called the Van Allen belts because he discovered them. Nowadays, we say the Van Allen belts, or more commonly, the radiation belts. It turns out that at the time, the Soviet Union had also detected the same thing, but had not published it in quite the same way or as quickly. So it turns out that space is full of these very high-energy particles. And this is a modern interpretation of that diagram, meant to simplify it, okay? So there'll be a quiz before we leave. But really, all what I'm trying to bring home is the Earth is in the center of this particular cartoon. And what it's trying to do is try and give you a cutaway. It's almost like a donut shape around the Earth. And this donut shape is filled with very high-energy particles. The Van Allen belt is very high-energy electrons and protons, subatomic particles. And we don't really know to this day how these very high-energy particles get in there. We know where the particles come from. It turns out that the Earth, at the center of this figure, the Earth's gravity is very good at holding onto the atmosphere, which is good news for us. But some of the atmosphere will be very hot and will escape off into the space environment around the planet. So gravity is still holding stuff in the vicinity around the Earth, but once it gets into space, it is ionized, so that the radiation from the sun that we've been hearing about, especially that extreme ultraviolet radiation, can break apart atmospheric molecules and atoms into their constituent subatomic particles. And so space is full of that, but once they get ionized and they're electrically charged, the Earth's magnetic field grabs hold of them. And the best way to think of it is a regular atom can move around anywhere relative to a magnetic field. But if you ionize it, so break it apart, and you're left with electrically conductive components, it becomes much more like threading beads on a string, where the string is the magnetic field. It hooks them on, and you can't get them off very easily. And it turns out that the Earth's magnetic field traps many of these particles in these donut regions around the Earth. And you can imagine the shape of the Earth's magnetic field. You can start perhaps to see how this might happen. But we still, to this day, don't know how they get to such very high energies, how they get so hot. And this is a cartoon suggesting that perhaps waves, so the constant buffeting of the solar wind going past the Earth's magnetic field causes it to wobble and breathe. And that motion of the field causes the particles threaded onto the field line to wobble. And just like a surfer picks up energy and momentum from a wave on the ocean, they take energy from the wave into the surfboard and get zoomed along. These particles might get accelerated by the waves. And that mechanism is still not very well understood today, and it's one of the key questions in space physics. And it affects an awful lot, not just the Van Allen belts. Here's another one of those easy diagrams. And this is really, all I want to do is show that it's a very complex system. We live underneath these magnetic field lines that capture energetically charged particles, which are accelerated by the solar wind, some of which will have come from the sun directly, and that some of them can then rain down the magnetic field lines into the upper atmosphere, and that's where we get the Aurora from, which we can talk about in a moment. But also, it can heat the upper atmosphere, drive winds in the upper atmosphere of 200 or 300 meters per second in the upper atmosphere. These energy interactions at the very top of our atmosphere couple energy downwards. It comes downwards and downwards, and it may interact with our weather and climate in some ways. And so Yvonne showed us some pictures earlier on of the frost fares during the Maunder Minimum, when the sun was very inactive. We know that there was a little ice age in Western Europe. The cutting-edge thinking on that is that solar activity can actually affect regional weather patterns slightly. And so that might also have accounted for what caused the Maunder Minimum and the Little Ice Age in Western Europe. But also it might not have done, and it almost certainly, unfortunately, doesn't have anything to do with climate change, which is majority down to us and our carbon dioxide. But it's a modulating effect on that. And so the connections of energy and material throughout the solar system are absolutely jaw-droppingly complex. So when you simplify them, they look like that. So the upper atmosphere is the interface with the space environment. And so what you're looking at here is the view from Tim Peake's office window until about last week. The view from the International Space Station, orbiting at probably about 600 kilometers above the Earth's atmosphere. And you're looking down at the northern lights glowing in this characteristic green and red color at between 1 and 200 kilometers above the Earth's surface. And what you're actually looking at there is atomic oxygen. So atomic oxygen, very similar to what you're inhaling in this room every time you take a lungful of air, is being bombarded by subatomic particles funneling down the Earth's magnetic field lines, raining down and causing and colliding with these atomic particles in the upper atmosphere. And it basically, that interaction between material coming from space and colliding with atmospheric particles causes some energy to be transferred from the incoming particle to the atmospheric particle. And basically, particles don't like having too much energy. They don't like being given lots of extra energy. They go into an excited state, which is usually unstable, and then they relax back to their normal background, boring ground states by dumping some light overboard, some radiation. And it turns out with atomic oxygen, if you clobber it with electrons from the space environment, at the temperatures and densities you get at the top of the Earth's atmosphere, then you get a characteristic green or red color. And slight changes in the density of the atmosphere and the energy of the incoming particles will give you both the green and the red color. So every time you take a lungful of air, you're sucking in an awful lot of what is basically the building blocks for the Northern Lights, if only it were at 200 kilometers altitude. And so we see these cartoons come up again and again in trying to show the kind of shape, usually not to scale, as we've already heard. The sun should be about 100 times larger in diameter than the Earth, and the distance between them here should be considerably larger. But what this is trying to show is that we live inside the atmosphere of our neighboring star. The atmosphere of the sun is continuously expanding outwards to form the solar wind, and we can track it all the way to the very edge of the solar system. So, as we heard a few minutes ago, the Voyager probes, which have reached the very edge of our solar system, can still detect the solar wind. So if you prefer to think of it as smoke, think of the smoke as if you think of the solar wind as smoke from the nuclear bonfire in the sun, that smoke smell gets all the way out to the very edge of the solar system. We can detect it with particle detectors we've built. And if you're wondering about density, we mentioned earlier, is space a perfect vacuum? Well, if you were to take a trip from the Earth and you just had a very tall stepladder and climbed up to the edge of the Earth's magnetic field and you were basking in the solar wind in hopefully a very good spacesuit, then just outside of your helmet, in a little sugar cube-sized volume of space, that's about 1 cubic centimeter, there would probably be somewhere between 1 and 10 particles, mainly hydrogen and helium nuclei from the sun, and then also some electrons, which overall would make it electrically neutral. So basically, smashed up bits of sun, there'd be about 10 particles just outside your spacesuit in a sugar cube-sized volume. If everyone can now imagine a sugar cube-sized volume at the end of your nose, without going cross-eyed, then you're probably talking about 10 billion atmospheric particles at room temperature and pressure at the end of your nose. So the 10 billion, 1 to 10. So it's very empty, but it's not completely empty. And it's that solar wind which really gives the shape of the Earth's magnetic field. And it compresses the Earth's magnetic field and some of the particles that are on it on the day side, the side facing the Earth, and on the night side, interactions between the solar wind and the Earth's magnetic field actually stretch it out into a long tail that conveniently isn't drawn here because it goes on for thousands of planetary radii, possibly, so a very long way over there. So we live inside a magnetic bubble, a force field, if you like. If you like to think of the Starship Enterprise, up shield Scotty, same deal. It's a magnetic force field inflated a little bit by particles from the Earth's atmosphere. And the Aurora sit around the magnetic pole, and so everyone I'm sure is an excellent geographer, but obviously we have North America, Greenland, and the UK is somewhere just off to the top right-hand corner. The Northern Lights sit in a region around the magnetic pole. This is another one of those false-colored images. This is a satellite image of the Northern Lights, recorded not in the green or red light that your eyes use. This is actually looking at ultraviolet light emitted from the Northern Lights. So the same kind of radiation that gives you a suntan, here being captured by a camera from above in space. And this part is just the day glow. This is the daylit part of the Earth's atmosphere when this image was taken. And so the Northern Lights sit in this region, this crown around the magnetic pole, called the auroral oval, and it's not just the North Pole. If you actually take a slightly different view from a satellite position over the Pacific, you can see there is a crown around both poles. So we have the Aurora Australis in the southern hemisphere, the southern dawn, and the Aurora Borealis in the northern hemisphere, the northern dawn. We're slightly racist. We talk about the northern lights mainly, and that's simply because that's where most of people live. That's where the indigenous peoples live, who've made up lots of legends about them. Down here you have lots of cold scientists and some penguins and not much else because Antarctica is uninhabited or has been for most of human history. And so we get these fantastic displays in the night sky through particles energized to very high energies in a particle accelerator, if you like, around our planet, firing material in. ultimately, that particle accelerator is plugged into the sun and gets most of its energy, or gets all its energy from the sun. And where do you see the northern lights? Well, you typically see them in this crown-like oval, but occasionally, space weather, if you like, is sufficiently bad or energetic that this oval, where we'd normally see the northern lights most nights of the year perhaps, gets pushed a bit further down to, say, the UK, or occasionally gets pushed further down to Central European latitudes, but only a very small percentage of the time. This is an image I got from the internet. It's not my data. I do believe those percentages are about right, and if anyone else thinks I'm a big fibber, and I'm sure people in the room probably do, these percentages look about right, please ask me in a question at the end, and I'll explain to you why I think those are about right. But you can get the northern lights up in the Arctic. Here they are over Lancaster University campus. Here they are in the southwest of the United States. So you do get them in some unusual places. And this is simply to show that this auroral oval moves. This is a part of the auroral oval captured by a meteorological satellite over just north of the UK on one night in 2005. And actually that allowed us to take photos of the northern lights over Lancaster University campus. But traditionally you'd expect it to be parked much further north, somewhere off the coast of the Scandinavian mainland. So we use a variety of tools to assess that. The aurora is actually in a really awkward place to access. It's too high to fly a plane through it, 100 kilometers. It's too high to fly a balloon through it. It's too low to fly a satellite through it, because the air is sufficiently dense at 100 kilometers that the satellite would just slow down through drag and then drop out of the sky, and people sue you, so we can't do that. But we can fly satellites above the aurora. We can build instruments on the ground to look up at the aurora from beneath, whether it's a radar or a camera, and we can study them remotely, and we then study how that links to the solar driver of this whole effect. And as we've seen already today several times, this solar driver is variable, it's not constant. Here we have the sunspot number over the last 6 solar cycles, or last 5 complete ones, and then the one that we're currently in now, which has actually proved to be a bit of a damp squib in terms of activity, but is nevertheless, we're coming out of the maximum, the most recent maximum of activity. So how does this affect us? Most of us in the room probably won't do this job. Some of us may, I don't know. But this is obviously one of the Apollo astronauts. Now, when you fly to the moon, you actually leave the Earth's magnetic force field behind. So you don't get the benefit of that magnetic protection. Some colleagues at the Rutherford Appleton Laboratory near Oxford did some analysis just to show what the radiation dose would have been to the Apollo astronauts during a series of high-energy emissions of particles from the sun. And what this is, as you can see along this little timeline, it's one of only a few graphs I've got in my talk, but 1968 up to 1973, almost at the end. And what it is each of these little sticks is showing the intensity of an outburst of solar energetic particles during the Apollo era. And then just to show you what that means in real terms, it's telling you what the dosage you would receive from one of those things we've been flying at the time in an Apollo mission. And it shows you what annual natural exposure we all get is, what it would be if you worked at a nuclear facility, what level it would be at if it were to induce short-term radiation sickness, and at what dosage it would be fatal. And you can see just up there, and I'll have to use my magic extending stick because I'm not tall enough. You can see up here in one of the Apollo missions, one of the final Apollo missions actually, was basically, the Apollo mission is here, 17, the blue line, Apollo 16 is there. Right bang in the middle of those, there was a solar energetic particle event that would have given a fatal dosage to the crew on board. And throughout the time, there were dosages that would have been given short-term radiation sickness. So flying a space capsule whilst throwing up is probably not very easy to do, or you're unconscious, so not very good for your health. So really, the Apollo astronauts were just very lucky. They missed all of these things, but it was luck more than judgment. And they were flying for typically a few days to get to the moon, maybe a day or two there and a few days back. So it's quite a short duration trip. But if you imagine going to Mars, you're going to be flying for 6 months to do that. You're going to soak up all of these. And so flying to Mars is a very different proposition than flying to the moon in terms of the radiation environment. So Mars, it looks like, is going to be an interesting place to go because space weather makes it very challenging. But Mars is also a rather interesting place because space weather has made it what it is. Space weather has turned it into a rather no-fun place to be. Because really, Mars has lost its magnetic field. It's lost its force field. It's a bit smaller than the Earth, and when it was formed, there was less heat created, and it's cooled down already. So that metal core that generates the magnetic field at the Earth, Mars has almost certainly got one, but it's frozen solid now. It's not moving. There's no magnetic field left. And so Mars has lost its force field, and the solar wind can get right down and access the atmosphere, pick it up, and blast it off into space. So over the last 4.5 billion years, Mars has lost its atmosphere that was probably rather like Earth to begin with, and it now has a very dense, cold atmosphere. And spacecraft orbiting Mars can detect the plume of material leaving Mars behind as the solar wind erodes it. So for life to develop on a planet, we need the magnetic field of the planet to act as a force field to save it from the solar wind. And we've already seen how planets around distant stars could be affected by space weather. So it's not just enough to find a planet. It's not enough to find one in the Goldilocks zone. We've probably got to find one in the Goldilocks zone with a strong magnetic field to keep it safe from the solar wind emitted from its star. We talked a bit about radiation belts. So this is how it can affect us every day now. The radiation belts look a bit like this. There's an inner and outer belt around the Earth. And if I superimpose an artist's impression of where the geosynchronous satellites are that do most of our communications, they sit at the edge of the outer radiation belts. And so if I say that some of the electrons in the outer radiation belts are sufficiently energetic that they're nicknamed killer electrons, you probably get the idea that some people think about this quite considerably, about what effect these have on satellites. And there is similarly an effect on satellites at low Earth orbit. The heating of the Earth's atmosphere, and again, this is a genuine distribution of what the satellites around in low Earth orbit look like around the planet. They're obviously magnified so you can see them, but there are lots of them. And when the space weather is active, when there are flares, when there are CMEs that strike the Earth, the atmosphere of the Earth gets heated up a bit, and it expands a bit. And as it expands, what happens is all these satellites suddenly find themselves in a bit of a thicker atmosphere than they're used to operating in. So they get a bit more drag, and they slow down a bit. And that means they go into a slightly different orbit. It's very rare they drop out of orbit, but they go into a slightly different orbit. And there are lots of things you can do. So this is a nice little chart showing in columns, in March in 1989, a count of how many satellites were not where they were supposed to be because of this kind of effect. And then the yellow curve shows us how bad space weather was. And you can see a few days of bad space weather, and suddenly a few thousand satellites are not where they're supposed to be. Now, if you're a government agency that tracks things floating around in space so that no one can lob a nuclear missile at you, not being able to account for a few thousand objects in low Earth orbit is kind of change of underwear time. So this is important for very military reasons, for our defense, and also spacecraft can collide. If they're not where they're supposed to be, they collide, they create fragments of debris. You've probably seen the film Gravity, which sort of starts that off as a starting point for the story. So interesting things can happen to satellites in low Earth orbit. And even on aircraft, your radiation dose goes up when space weather is bad. They reroute to not use polar routes when space weather is bad. Modern spacecraft are operated by computers. The pilot is commanding a jury of computers to decide to tell the plane what to do, and they control the parts of the aircraft, whereas 30 years or 40 years ago, there was a wire between the pilot and the control surfaces that was invulnerable to space weather effects. Well, computers may be more so. So we have to be very careful about how we do some of these things in the world of space weather. And really, just to finish off, my final point I'd like to make is, there are some people asking, the Northern Lights are saying the Northern Lights are beautiful, but space weather could be risky. How bad could it be? And as Lindsay already mentioned, we know there was an event in 1859, this Carrington event, and here is the paper that Lindsay referred to, where we saw an absolutely enormous solar flare and a massive coronal mass ejection, we now know, traveled out and hit the Earth. Well, this was a big event. So if we're thinking how bad could it be, that's probably the benchmark we should go for. And here are some contemporary accounts from newspapers at the time, and we won't read them all out because we don't have time, but they're quite good fun. Some of them talk about red lights, the Aurora Borealis over San Francisco for several nights running. This one talks about the aurora being so bright that birds were rising from the trees thinking it was morning, thus allowing these citizens of New York to go and hunt them with rifles in the middle of the night. And then basically travelers in the Rocky Mountains sleeping outside. So these were people who knew what the outside world was like, arguing over whether it was breakfast time because the northern lights were so bright over the Rockies. So these were big space weather events. And we saw, Lindsay had that great cartoon of the telegraph operators being electrocuted and some fires being started, and that indeed was the case. There was some damage to the Victorian internet. But the good thing, of course, about the telegraph system was we have a record of the conversation at the time. And I just want to share this with you. It's a conversation between the Boston and Portland operators of a telegraph line, so a long way apart with a copper line connecting them. And what we see is, well, I can show you their conversation. It goes a bit like this. And I'm assuming everyone can read Morse. I might need a few more minutes then, Jocelyn. So what they actually say is, one says, please cut off your battery entirely from the line from 15 minutes. And the one at the other end says, I've done it. It's now disconnected. In other words, I've turned everything off. Using the system he's just turned off, he sent that message. Okay? So the reply is, mine's disconnected, and we're working with the auroral current. How do you receive my writing? And the reply is, better than with our batteries on. The current comes and goes. And what's happening is these disturbances in the space environment are changing the magnetic field at the surface of the Earth due to currents flowing through the upper atmosphere. And those wobbling magnetic fields at ground level are inducing electrical currents in the copper wires. And sometimes the current's going in the same direction as the current they're trying to push along with their batteries, which makes it too strong. And sometimes it's going the other way, and it's kind of nullifying their batteries. So they agree to leave their batteries disconnected, and they basically say, well, should we just carry on without the batteries while this is going on? And they say, yeah, very well, we'll go on with batteries, let's go ahead. So this system actually carried on, just being powered by the current from the Northern Lights, if you like. Although, back in that time, 1859, that was state-of-the-art transport. Nowadays, of course, we look a bit different. Other train franchises are available. But there are semiconductors in here, there are computers, there are long-conducting power lines, there are signaling systems, there are things that talk to satellites in orbit. Technology has moved on. And that's just really what I wanted to end on, really, with this and the next couple of slides, is that space weather's always been there since the beginning of our solar system. But we've engineered ourselves into a place where we might be a little bit more vulnerable to some of the hazards. And so power systems especially might be vulnerable. Large conducting copper lines, you get the same effect you might get with a telegraph system, where you could damage, a very large event could damage a significant fraction of our power grid. So what the worry is if you lose your power grid, say, and I know this because I come from Lancaster, where Storm Desmond arrived in December and took power out for the city for 70,000 homes for basically 5 days. What you've realized is that when the power goes, it's inconvenient at first because the lights go off, but then you realize your car's going to run out of petrol, and the tills and the petrol station won't work, and the supermarkets can't get any deliveries because there's no petrol to put in the trucks, and the wastewater plants stop working because there's no electricity, and it hasn't come back after 7 days because you've actually damaged the power grid. And then, well, how do we refrigerate food and drugs? And then how do emergency services last? Because they surely have generators, but they'll last for a week and they won't last for a month. So if it took a long time to repair the damage from a space weather event, how do you cope with it? So this is some real project fear. But do not worry. If you see me in the car park afterwards, I can sell you a solution. There are people actually genuinely trying to sell you solutions to this problem, but I ignore most of them. And so I don't want to end with a don't have nightmares. What I want to do is point out this is just another one of those things our society is probably going to have to deal with. High-impact, low-frequency events, or the black swan events, as Lindsay said. Things that occur that are massive, but occur so irregularly that we're not set up to deal with them. And you'll be pleased to know that actually volcanic eruptions, earthquakes, pandemic flu, tsunami, the government worries about all these things and has a national risk register, talking to experts in those various fields about how best to prepare and what we should do. And believe it or not, the British government, whatever flavour it has a document which outlines where space weather is, where extreme space weather is on this sliding scale of risk. And they talk to experts in industry and from academia to plan how you might deal with that. So most of the companies I've been talking about, electricity companies, rail operators, aircraft operators, they all have contingency plans for what to do in different space weather circumstances. So you shouldn't have nightmares, but you might never realize that an airline operator would actually be thinking about the state of the sun in some of their operations. And so finally, just to leave us on a very beautiful point, it's not just planet Earth. So here we have Saturn, seeing the beautiful northern lights around the magnetic pole of Saturn with an image from the Hubble Space Telescope. This is ultraviolet aurora around Saturn's magnetic pole taken from the Hubble Space Telescope, superimposed on an image of the northern lights from an image of Saturn from Cassini, an orbiting space mission. So it really is a ubiquitous phenomenon we see throughout the solar system and possibly occurs throughout the universe and is an indicator of how a planet may or may not interact with its environment and even how it may be able to support life. But finally, how do you see the Northern Lights from the UK if you don't want to go on a holiday to the Arctic? Well, it occurs quite rarely in the UK, perhaps a couple of times. A really good display might be a few times a decade if you live down south, and the northern part of Scotland a few times a year, and everywhere in between, somewhere in between those kind of numbers. Well, this is a photo, again, taken from the Lake District on New Year's Eve last year. But people get to see these Northern Lights displays often because they've got some sort of alert service. So I'm going to finish on a plug. If you're interested in getting alerts when magnetic conditions on the Earth are sufficient that you might see the Northern Lights from the UK, then just go to your favorite search engine and type in Aurora Watch UK. And it's a service we run from Lancaster that takes real-time data and does what we call nowcasting. And what it does, it basically shouts to you via email or Twitter or Facebook, there's some disturbances now, it might be worth going outside. It might be worth leaving the curtains open, or before you go to bed, going into the garden and having a look upwards, rather than hiding behind the curtains that night. So if you want to tip your odds a little bit in your favor from the UK, this tells us when coronal mass ejections arrive at the Earth and trigger the kind of disturbances that cause the Northern Lights to migrate from their usual position somewhere north of Scandinavia to somewhere perhaps north of Scotland, where you might have a chance from seeing them. So good luck with that. Do sign up. It's all for free. Thank you very much.
Thank you very much, Jim, for a fascinating and sobering talk. We've got time for a couple of questions before I ask Charles Jenks to do the closing note. Yes.
It's not about Mars bars, is it?
I missed the first couple of talks. I only saw the last two talks, so if this question's been asked already, forgive me. I was just wondering about the planets and moons are pockmarked with meteor strikes. Is the sun struck with meteors?
The sun is very good at sucking things in, so it's huge gravity. So comets especially, on those kind of movies we see where you're looking at the sun over several days or months, you can spot sun-diving comets in nearly all the time. They're very, very common. So the sun is still hoovering things up. It's cleaning up the solar system for us.
Thanks very much for a most fascinating talk. I noticed that in 1859, the telegraph operators seemed to know what the source of their problem was straight away. And that was only maybe, say, 15 years after electric telegraphs were introduced. So was that a very early observation that the Aurora was causing problems for telegraphs?
Yeah, I think if you imagine the geography of the United States, and a lot of it was in the United States, then those lines which went up into the quite high latitudes, I think they were probably used to dealing with it. The operators could see that when the Northern Lights were very bright, I mean, not at the level that they went to San Francisco or this crazy stuff like that, but at those high latitudes where they were used to seeing the Aurora, I think telegraph operators realized that there was a correlation just from their experience between the Aurora and their telegraph operations. So they would call it the auroral current. They couldn't quite explain it, but they knew it was there.